All right, friends, 3 o'clock. Welcome back to your favorite class. That's right, dynamics. Yes. A lot of announcements I got to go through really quick. First is that we're not going to have formal lecture tomorrow. All right. We're pretty far ahead on what we need to do. I'm basically going to finish the material for the course today. Like, we're going to finish the last little bit of material today. Isn't that exciting? All right. So tomorrow, give you guys a break, take the time, work on simulation number 3. I'll come here into this lecture space for questions. If you have questions, kind of hold it like an office hours, but people can come and go as they please, and I'll just kind of answer questions as people have them. So there's that. So tomorrow, chill day. I'm trying to like chill. All right. You guys got a lot going on the next like week and a half, probably with other classes, trying to pack all that stuff in there, and we're ahead of the curve. So I'm chilling. All right. So take time, work on your simulation, and work on your homework. So with that said, simulation number 3, which is on linkages, which we talked about finished up like a week ago, that's due on Friday. I've also posted a homework now on gears and gearing systems, which is on Blackboard, and you can take a look at that. That'll be due on Tuesday. And after today's lecture, you'll be armed to the teeth, rawr, to work on that particular assignment. All right, so get after that. And that's it for formal material that we have for the class. And then next Thursday is your last exam for the class. So last exam is going to be on the 3 topics that we've kind of covered the last couple of weeks, and that is linkages, gearing systems, and conservation of momentum. So that's all we got left. We're nearing the end. Our time is nigh. It is near the end, friends. All right. Is there any ado? How do we like the meme today? I think I may have shown this one in the past, but I seem to have like the SpongeBob theme going, all right? American students, so they have to take a test, but the form of measurement is not football fields. So frustrating. It's funny when people like do exams and like get an answer of like a length of 14. I'm like, wow, 14 what? Football fields? No, I don't actually think that, but maybe that's what you guys think. I don't know. All right. Without further ado, let us get on with it. Gearing systems, yes. And don't forget to sign up for my classes. Unless you hate me, then don't sign up for them. All right, gearing systems. Last time we kind of talked our way through the mathematical relationships behind gears. And we had the most simplistic model to start, which was 2 gears that were kind of connected in a series. And so here's gear number 1 and gear number 2. They're connected at that particular point, which we call the mesh. And let's say that this is gear number 1, pivoting about the center, gear number 2, pivoting about its center. This guy is rotating with some angular velocity here, which is like omega 1. This guy is rotating around with some angular velocity here, which is like omega 2. And these gears have radii of their pitch circles, which this guy is like R2. This guy is R1. All right, R2 with the diameter of D2, R2, D2. Very favored with engineers. We know that at the point where these 2 guys are in mesh, are in contact with each other, they will share a velocity, and we generally do that here as like our velocity v. So we know that the magnitude of that velocity is going to be something like omega 1 times R1, same thing as omega 2 times R2. Our most simplistic relationships, we know that we're in contact with each other, they share that velocity, this is what we get. We can rearrange this and rewrite this to get a general relationship that exists between any 2 gears that are in mesh with each other that are moving together. And that is a relationship that we call the velocity ratio. And it is the ratio of the output angular velocity to the input angular velocity. So here, this is something like omega 2 divided by omega 1, which is the same as d1 on d2, which is the same as r1 on r2, which is also equal to n1 on n2. So a lot of information that we sort of presented in last class with basic relationships that exist between just 2 gears in a train. Choo-choo. This is velocity ratio. Here is your angular velocities. here is your pitch diameter, pitch radius, and here is number of teeth. So all these general relationships here now we have to work with. So if I give you some information about the number of teeth and I ask you for angular velocity, you can do that. If I give you information on pitch radius and the velocity ratio, you could figure out other stuff. Okay, so all these relationships are useful when you're going to calculation between two gears in a train, the most simplistic relationships that we have. And these mathematical relationships that we sort of developed between two gears are the foundation for what is the fundamental law of gearing, tenet number 1. Remember when we talked about the fundamental law of gearing, there were two tenets, and the first is related to the equation that we have here. And so this is related to fundamental law of gearing, part 1. All right. Fundamental law of gearing, part 1. There's a second part that is not really of concern to us. Deals with the pressure line and pitch point and some things related to stresses on gears, which not really that important. So you saw it once. Now dump it out the other side of your brain because you're not going to really use it the rest of this class. All right, so there you go. So we made it to the fundamental law of gearing, part 1. So we took this idea of like two gears in a very simple train and extended it to, well, what if we have a bunch of gears that are in a line? And we called that bunch of gears in a line a simple gear train. And we developed a little bit more math from there. All right, our train's getting a little longer. Choo, choo, choo. Rawr. And here was our simple gear train. Looks something like this. Bam! We had a bunch of gears in series. Each gear has its own shaft. 1 gear per shaft. Right? This is not to be confused later with the compound gear trains where we have multiple gears on the same shaft. All right. We extended the fundamental law of gearing to the system of shafts by saying that the velocity ratio is constant between any two gears in the chain. So developed the more general relationship between two gears in this train, which was that the angular velocity ratio between any two gears in the train I and J is related to the number of teeth or the pitch diameters of gears I and J. So here we saw that like the angular velocity of gear J divided by the angular velocity of gear I is the number of teeth of gear I on the number of teeth of gear J, which is the same thing as the diameter of gear I divided by the diameter of gear J, same thing as the radius of I divided by the radius of J. All right, so those relationships that we developed for two gears in a train hold for a gear train that has many, many gears in this simple arrangement. All right. So this is what we saw for simple gear trains. Now, in reality, those simple gear trains are like almost never seen in practice. Okay. Rarely is the case where you just have like these series of gears that happen to coincide with some shafts that need to have some output velocities that are happen to be related to the distances between them perfectly to get you what you need. That's like never happens. Okay. If it is, it's like a magical happening of engineering. Okay, so in reality, what we see in engineering more commonly are these compound gear train systems, which are potentially more useful. So some of the complicated or compound systems that we see in real life begin with the math behind the simple compound gear train. All right, so compound gear trains. Oh, it looks like I have a comment and or question. Hamburgers per pound gallon is better. Agreed. So compound gear trains looked something like this, where now we have more than one gear per shaft. So glad I don't have to draw this on the whiteboard. Man, it's actually really nice to just be able to like copy and paste this one in there, because believe me, trying to draw this on the whiteboard when I used to have to do it, oof. No, thank you. All right, it's my inner Jim Carrey. All right, at least one shaft with multiple gears. And we see that here with this sort of central shaft here. It's got 2 gears on it, number 3 and number 4. All right, so what is the math behind this? Well, the math behind this has to do with the gears that are driving the system and the gears that are being driven. So let's clarify what we mean by that. If we look at this compound gear train and we think about number 2 as being the pinion gear, so this is the input shaft, so this guy here is the pinion, and it's kind of driving the system, then we would say that gear number 2 is driving gear number 3. All right, so 2 is driving and 3 is driven. All right. Now, that's pretty easy to see. There's always this driving gear and always a driven gear. And if we thought about removing the gears that are on the back end of this compound gear train and just thought about looking at what is the system going on here between 4 and 5, well, if we just had 4 and 5, again, there's this idea of there's one of them that's driving and one of them that's being driven. And the same kind of idea would hold, is that in this situation, it's like 4 is the driving gear. And here is the gear being driven. All right. So again, it's like this, I'm in control and I'm controlling you. So if all of this stuff on the back end wasn't there, then you'd have to pick like which one is driving and which one is being driven. Well, information from upstream is given to us, like with gears 2 and 3, and that's the information that's feeding into number 4. So it's like we're driving number 4, and then 5 is being driven from that information. So we have a series of like gears that are driving the system and a series of gears that are being driven in the system. So it's easy to see that like 2 and 4 are driving, and 3 and 5 are being driven. At least that's how we would look at the general idea here. So what we did when we brought this compound gear train into our analysis is we looked at, all right, what is the output angular velocity of this compound gear train given a certain input angular velocity? So what is output omega given input omega? Or mathematically, that is, what is omega 5 given omega 2? This is what we were interested in doing. And so we went through a kind of a rigmarole to show that there's this very special relationship for compound gear trains where we have that the output angular velocity is the product of the number of teeth on the driving gears divided by the product of the number of teeth on the driven gears multiplied by the input angular velocity. So we saw the following relationship, and that is omega 5 plus n2 n4 on n3 n5 times omega 2. Where here this is number of teeth driving gears. Here this is number of teeth driven gears. All right. This is specific to our situation here, where we have a 2-stage compound gear train, so one in the back, one in the front. But we can apply this general idea to all of these compound gear trains. And so we said generally, for compound gear trains, we had something like the output angular velocity omega j divided by the input angular velocity omega I is the product of number of teeth of driving gears divided by the product of number of teeth on driven gears. All right, and this was a relationship that we found generally for compound gear trains. Right. So that's about where we left off last time. I know I did about 10 minutes of recap there, but I think it's good to kind of get our bases before we attack a problem again. So let's do an example problem. We're looking at one of these compound gear trains, and let's make it a complicated one. So we're going to bring in a 3-stage compound gear train and do the analysis here. Let's do that. We're getting cray. But you guys can do it, all right? You're the smartest engineers in your chair. As long as no one else is touching your chair. Okay. All right. We're given some information here with this 3-stage gear train, okay? So here's stage 1, stage 2, stage 3. It's a 3-stage compound gear train. We're given information about the numbers of teeth on each one of these particular gears. So 2, 4, and 6 have 14 teeth. We're kind of like showing that here with this 14 lowercase t for each one of these driving gears. Remember, 2, 4, and 6 are driving the system. We see N3 and N5 has 84 teeth. All right, so it's like a whale shark. And N7 has 70 teeth. So this guy's got 70 teeth. So given information about the number of teeth on these gear and the input angular velocity, we want to find some pieces of information. That is specifically the angular velocities of gear number 5, gear number 7, and finally the gear ratio of this particular gear train. All right, makes sense. We want to know what we're getting out given what we've put in. Obviously, that's what engineers do. All right, so let's do this. We know the relationship between the ratios of the angular velocities of any two teeth is the product of the number of teeth driving the system divided by the product of the number of teeth being driven in the system. Okay, so the first thing we want to do is identify which ones are driving, which one are driven. So here, 2, 4, 6 are driving. 3, 5, 7 are being driven. 357, my favorite clothing store. Only the ladies in the audience might get that one. All right, 2, 4, 6 are driving. 3, 5, 7 being driven. All right, that's sort of obvious to see. 2, 4, 6 driving. 3, 5, 7 being driven. And we could think about it by like just looking at the individual stages of the compound gear train. Like if we got rid of all this stuff and just looked at this guy, well, 4 is driving 5. If we got rid of all this stuff and just looked at this one, 6 is driving 7. Right? So 2, 4, and 6 are driving. The rest are being driven. Now, the first thing we're asked about is omega 5. So we need to just isolate the first 2 stages of our system. So when we're looking at omega 5, we're going to isolate 2 through 5. So we're going to isolate just the first 2 stages of this gear train. Right. We're interested in what's going on with this guy. All right, the angular velocity of gear number 5, which is going to be the angular velocity of gear number 6 because they're on the same shaft. Right. So if we do that, then the general relationship to find the angular velocity of gear number 5 is going to be the product of the teeth, which are driving to get to gear number 5, divided by the product of the teeth that are being driven up to number 5. It's going to be something like N2 times N4 over N3 times N5. You don't incorporate 6 and 7 because we haven't gotten to those in our gear train yet. All right, this is all multiplied by the input angular velocity omega 2. So this is how we use this general relationship to come up with the angular velocities of the various components in this compound gear train. Right. So this is easy. We can now just plug the numbers in because we have all of this. Omega 5 is N2 times N4. Both of these have 14 teeth, just like me and my cousins. 14 teeth for 2, 14 teeth for 4. N3 has 84 teeth. N5 also has 84 teeth given in the problem. They're whale sharks. 3 and 5 got a lot of teeth. Shamu! And then omega 2 given to us as 300 radians per second in the problem. So because of the relationships that we know with all these various teeth, etc., we get that the angular velocity of gear number 5, 8.3. Repeating, of course. Radians per second. That was a throwback to Leroy Jenkins. 8.33 repeating, of course. Anybody that gets that, wow, that's kind of a complicated joke. All right. Mega 5, 8.33 radians per second. So we're putting in 300. And because of the arrangement of the teeth on our particular system, we're getting out on gear number 5, 8.33 radians per second. So pretty big step down in the angular velocities from 2 to 5. All right. Now we also want to know what is the angular velocity of gear number 7 in the train. All right. So ultimately we want to figure out what is the angular velocity of this output shaft in the very end. So the same general idea is going to apply here. Product of the teeth on the driving gears. Now we bring in 6 and 7 because they're now part of the chain. And away we go. 2, 4, and 6 all have 14 teeth. So I'm going to do 14 times 14 times 14. If you want to do 14 cubed, that's all right. I understand. And then gear 3 and gear 5 have 84 teeth. Let's give it in the problem. And gear number 7 has 70 teeth. Why has it got to be so different? He's a unique flower. Multiplied by my input angular velocity, 300 radians per second. Work this through. You'll get an angular velocity of the output shaft here. It's going to be 1.67 radians per second. Whoa. Took my slider bar with me. Okay, an interesting find. So because of the way that we've arranged this compound gear train, we're supplying 300 radians per second and getting out 1.67 radians per second. 300 on the input side, 1.67 on the output side. So we're reducing the angular velocity of the system by some factor. And the last part of the problem is asking us to figure out what is the factor of reduction of this angular velocity from the input to the output shaft, aka the gear ratio. And remember, the gear ratio is the ratio of the input to the output. So here, the input is omega 2, the output shaft is omega 7. So the ratio of the input angular velocity to the output angular velocity is 300 radians per second divided by 1.67 radians per second. Or you'll see here a gear ratio of 180, or more commonly reported as something like 180 to 1. It's a more common way to report the gear ratio. So this gear ratio here, 180 to 1. We put in 180, we get out 1, or the linear equivalent of that. So if I put in 180 RPMs into my input shaft, I get 1 RPM in my output shaft. If I put in 360 RPM on my input shaft, I get 2 RPM in my output shaft, right? It's a general idea of the gear ratio here. Most people like to think about shafts and these gearing systems in terms of the gear ratio. It's the input divided by the output. And remember that the gear ratio is the input or the inverse of the velocity ratio. So I got to keep those two terms sort of separate from each other. One final thing that I haven't really brought up yet and I want to talk about is sometimes you'll see in data sheets or in some gearing system catalogs a negative sign in front of the gear ratio. And your book doesn't use this nomenclature, but I'm going to do it just so that you're comfortable with it and you have seen it. And when you see a negative sign in front of a gear ratio, that means that the direction of the angular velocity of the output shaft is different than the direction of the angular velocity of the input shaft. So let me write what I mean in words. So if gear ratio is negative, direction of output shaft, angular velocity, is opposite of direction of input shaft, angular velocity. All right. And I stick with this nomenclature through the homework and through the problems that I work. And I think that's a good thing to do and get in the habit of it because it can communicate information appropriately. In the real world, a lot of people don't do that. So if someone tells you a gear ratio of 180, well, maybe the input and the output shafts are rotating in different directions. Maybe they're not. You don't know. Okay. And you can't assume to know. But you know that the relative magnitudes of their angular velocity is that gear ratio. So that can be helpful. Now let's look back at our problem and determine if we should use a negative sign here or not. All right, so we've calculated the gear ratio as 180 to 1, but do we need a negative sign or not to be appropriate? Let's look. All right. So here's our 3-stage compound gear train. And we're told that this guy has an angular velocity kind of in this counterclockwise rotational direction to start. So I'm going to assume and draw that here is my counterclockwise angular velocity for omega 2. All right. So to match that, omega 3 has to be the opposite direction. Omega 4 has to be the same direction as omega 3 because they're on the same shaft. To match that, this shaft has to be rotating in this general direction. And then to counteract that, number 7 has to be rotating in that general direction. Okay, so we have the output angular velocity here, the input angular velocity here. And notice that omega 7 and omega 2 have opposite directions in this particular gear train. So it would be appropriate for us in this particular situation to indicate that the gear ratio is negative because the directionalities of the angular velocities of the input and the output shaft are in different directions. So it would be most appropriate for us to put this gear ratio here, not as it currently stands, but to include a negative sign in front. Notice I left a little space there for the negative sign. God damn. Clever. All right. So this is the appropriate gear ratio for this particular problem, negative 180 over 1. And that's because we're indicating to whoever is looking at our particular analysis that the output angular velocity is different direction than the input angular velocity. And if you put in 180 RPM, you're going to get out 1 RPM in the other direction. Capiche? Capiche. Last thing I want to talk about is the most complicated gear train that we'll talk about in this class, though in real life, gear trains can be pretty complicated. And the last one that we're going to talk about in this class is the reverted compound gear train. All right, so here we are with our reverted compound gear train. Bam. And let's talk about what distinguishes this from just a normal compound gear train. All right, I'll give you a second to digest this picture and kind of digest what's happening. All right, so here we have our input shaft. So this is our input angular velocity that we're going to apply to this guy, and it's sort of driving this particular gear and shaft combination. That is going to drive this guy here, right? this sort of second gear in the chain, which is given by N3, is attached to what's called the counter shaft. The counter shaft contains two gears on the same shaft, and so it counts as a compound gear train because we have two gears on that one particular shaft. All right. Now, this counter shaft contains a second gear to it that will then drive a fifth gear in the series. And the reason you would want to use or sort of make a reverted compound gear train is because the input and the output shafts are along the same axis. So we see that here in this particular picture. The input and the output shafts are both along the same axis. This is particularly useful in quite a bit of engineering applications where you have one shaft that is rotating here and you need to slow the rotation of that shaft down along the same axis, right? Your automobile does this. So anyone that's, driven in a standard automobile, the transmission inside of your car is using this general idea. There's one shaft that you're using to transmit all of your power, and the gear ratio that you're switching into, first gear, second gear, third gear, fourth gear, is giving you a different gear ratio between your input and your output shaft. So when you switch from like first gear to second gear to third gear, so on and so forth, what you're doing is you're switching the ratio of the gears in that counter shaft. Basically, you're taking the counter shaft that you currently have, which is attached to your main shaft, switching it out for another counter shaft to give you additional changes to your gear train. All right. So this is the way that automobile transmissions generally work. All right. So counter shafts, important. So let's draw some definitions and let's put some stuff down on the paper here. All right. Let's put ink to paper. All right. Let's put pixels to paper. We'll say that these reverted compound gear trains input and output shafts are along the same axis. All right. This has uses in a lot of engineering applications. All right. Have you ever used a hand drill and twisted the little top on it that switches the speed of the drill? What you're doing there is you're changing the counter shaft gear ratio. Okay, so you've got some motor power that's driving the drill bit, and when you switch that little switch on the top that drives the drill bit, and you switch that to give it a slower or a faster speed, giving you more or less torque on your bit, what you're doing is you're basically changing that reverted compound gear train. You're switching out the counter shaft to give you more or less rotation on your drill bit, given the same input from the motor that's inside of the drill. All right, so some handy dandy little stuff there. Very common in application. All right, so input and output shaft along the same axis. If you make a reverted compound gear train, it's still a compound gear train. So the equations that relate like number of teeth to input and output angular velocities, yada, 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 that we talked about for general compound gear trains hold. So compound gear train equations still hold. So for this particular example, you have something like the output angular velocity omega 5 is n2 times n3, n2 times n4 over n3 times n5. All right. So 2 and 4 are still driving, 3 and 5. Right. So product of the teeth on the driving gears divided by product of the teeth on the driven gears multiplied by the input angular velocity omega 2. That equation, still good. Just like the fish that's been in your fridge for 16 weeks, still good. All right. There's one additional relationship that comes up when you have these reverted compound gear trains, and that is that the center to center distance between the two shafts must be consistent. All right, and that is the radius of gear number 2 plus the radius of gear number 3 has to be the same as the radius of gear number 4 plus the radius of gear number 5, right? These center-to-center distances, let's get my eraser going here, this guy here, this guy here, this guy here, this guy here, they must be the same. So the distance between the centers of gears 2 and 3 must be the same as the distance between gears 4 and 5. And that's what we have with this general relationship here. The radius of gear 2 plus the radius of gear 3 equals the radius of gear 4 plus radius of gear 5. And this could have many forms, not necessarily just this relationship, but the diameters also have to have the same general feel. And if you substitute diametral pitch into this particular guy, and it will cancel out, and you will still end up with something like this. N2 plus N3 is N4 plus N5. So there you go with your relationships. If all same diametral pitch, this relationship holds. All right. This is always true. This holds only if they all have the same diametral pitch. All right. There we go. Away we go. And that just comes up because you need these shafts to be at the same distance apart. Otherwise, if one gear is bigger than this relationship would hold, then some of the gears aren't touching each other. One of the sets is not going to be able to touch each other. All right. Let's see an example with this reverted compound gear train. Okay. Here we have a reverted compound gear train with a gear ratio of 18 to 1. All right. Given information about this particular guy, that means an input of 18 gives me an output of 1, shafts rotating in the same direction input as they are at the output. Okay, because it's a positive value. Gears 2, 3, and 5 are visible on our train, and we can count the teeth on each one equal to 16, 96, and 84. Okay, useful. We want to determine the angular velocity of the output shaft if the input shaft is rotating at 90 radians per second, and the number of teeth and angular velocity of gear number 4. So we're in some engineering situation where we can access gears gear 2, 3, and 5, but for some reason we're restricted and can't see what's going on with gear number 4. And maybe we need to know like how many teeth are on gear number 4 so that I order some replacement parts and have some at the ready. Okay, we can use like engineering to do the calculation. We don't have to bust this entire thing open to look at gear number 4. You know, this situation happens in engineering all the time. So the first thing that we'll want to notice is that the gear ratio is 18 to 1. And we're also told that the input shaft is rotating at 90 radians per second. All right, so straight away, I can do a calculation about what is the angular velocity of the output shaft because I have the gear ratio and I have the input angular velocity. So remember, my gear ratio is the ratio of the input angular velocity to the output angular velocity. All right, so if I want the angular velocity at the output, that's just going to be equal to omega2 divided by the gear ratio. So here, the input angular velocity is 90 radians per second. And the gear ratio is 18 to 1, or when we use in calculation, it's 18. And I'll get that the angular velocity of the output shaft is 5 radians per second. So we see here that we have a reduction in the angular velocity of this particular system. It's moving slower on the back end than it is on the front end. All right. Now, we also want information about the number of teeth and angular velocity of gear 4. Okay, well, we can use our compound gear train relationships that say something like omega 5 is n2 times n4 over n3 times n5 multiplied by angular velocity of the input shaft omega 2, right? Driving gears, driven gears, input angular velocity. All right, it's general relationship, going to see over and over and over. The only unknown that we have in this particular situation is the number of teeth in gear number 4. We just solved for omega 5. Omega 2 is given to us, and we know all the teeth on 2, 3, and 5. All right, so we can solve for N4 by just sort of plugging things in directly here. Okay, so plug in. We'll do the glade here. Plug it in, plug it in. Omega 5 we just calculated. 5 radians per second. You could also identify that omega 5 divided by omega 2 is the gear ratio, or sorry, the velocity ratio. N2, number of teeth on gear number 2 is 16. N4 is our unknown. Number of teeth on gear number 3 is 96. And the number of teeth on gear number 5 is given to us as 84 in the problem. This is multiplied by the input angular velocity, which was 90 radians per second. Can solve this and determine that the number of teeth on gear number 4, 28. If you're doing calculations on a test, you're doing calculations on a homework, and you get something like n equals 0.7, you done messed up, all right? You're not going to have a gear with 0.7 teeth, okay? Maybe your first cousin from West Virginia has 0.7 teeth, but you ain't got any gears with 0.7 teeth, all right? So this gear, 28 teeth. Last thing that we're asked about for this particular problem is the angular velocity of gear number 4. All right. Also need this particular angular velocity. Because gear number 4 is attached to gear number 3, here on this counter shaft, we know that they're going to share an angular velocity. So really the only analysis that we need to do is between N2 and N3, because if we figure out the angular velocity of gear number 3, then we have figured out the angular velocity of gear number 4 since they're on the same shaft. All right. Omega 4 equals omega 3. That's because same shaft. All right. And so let's do our analysis between gear 2 and 3. And our general relationship here holds when we're looking at the relationship between two gears in a train. And that is something like omega 3 divided by omega 2 is N2 on N3. It's our first fundamental law of gearing. All of this information we have except for omega 3, so we can rearrange omega 3. Get your omega 3s, N2 on N3 times omega 2. Number of teeth on gear number 2 is 16. Number of teeth on gear number 3 is 96. And omega 2, given in the problem, 90 radians per second. So if we're interested in the angular velocity of gear number 3, which is the same as the angular velocity of gear number 4, this can be calculated with the algebra as 15 radians per second. All right. There you go. Algebra, pretty easy for these guys. You just have to sort of understand what are the relationships between all of these guys. You know, what's the gear ratio, what's the velocity ratio, number of teeth, pitch diameter, diametral pitch. These vocabulary words mean things mathematically that you just have to like be ready to use and be ready to execute with. All right, so you're armed now, with all the tools that you need to calculate and go through homework number 6. Is it 6? Yeah, 6 on gears, which is the last homework for the class. So I will be around for office hours tomorrow. Reminder, no lecture tomorrow. And I will help you with homework questions, with simulation questions. So give those a go. And maybe I'll see you tomorrow, maybe I won't. And we'll hold lecture as normal on Friday. So see you then.